Hello, we are group number 11. My name is Mastrapa.
I'm Aaron Solomon.
And I'm Javier Seoane.
And we had the pleasure of working on two projects together, and we're going to cover the first one first, 4-bar mechanism analysis. Before I get into our particular 4-bar, I would like to describe what exactly a 4-bar is. It consists of 4 links. There's something known as the Grashow rule, which basically says that if the shortest link plus the longest link are less than the addition of the other 2 links, then it is a type 1 mechanism, which means it's one of these 3. If not, it would be a type 2 mechanism, which falls under a double rocker mechanism. In our particular example, we had a crank rocker mechanism, which basically the crank, or the shortest link, is connected to the stationary link, the constrained link. That way it provides 360-degree motion from the shortest one. But for our particular example, we had our 4th link, which was the longest one, as our input variable. And we then deciphered the displacement, velocity, and acceleration with analysis, and then we got the coupler link trajectory. As you can see here in this example, our 4-bar has very limited mobility when we have the 4th or the longest link as our input variable, because it can only travel a certain amount of distance. Now my friend Aaron's going to finish up on 4-bar.
Okay, so as Ray previously stated, the 4th link here was our input link. And after calculations, we saw that the link only traveled through an angular displacement of 170 degrees to about 218, which therefore explains why the system rocked back and forth. This trajectory of the extension link is shown in the next slide. As you can see here, it starts at this position, and as the velocity continues, it goes along this trajectory line. After that, we have 2 other graphs displaying the angular displacement and the angular velocity versus the angular acceleration and the angular velocity versus the angular displacement. Okay, so for project 2, we synthesized the slider crank mechanism, and a slider crank basically transforms linear motion into rotary motion. It's a useful mechanism commonly used in the real world today. Systems such as pistons or gearing systems use the slider crank all the time. By synthesizing this slider crank, we furthered our understanding of industrial machinery and its operations, and it assisted us in improving slider crank mechanisms that might be used today.
You can see here a visual representation of the slider crank mechanism. As this slider moves up and down, linear motion is converted into rotation of this crank arm. Now, as you can see, this arm, known as link 2, is much shorter than this arm, known as link 3. That allows the system to completely rotate without any singularity points, which would cause lockups. Like, per se, if this slider came down and were to meet with the origin of the mechanism, it could cause problems. Here we have our results, and this is a plot of the C point. Now, C point is basically linear. It's the points that the slider traces as it moves along its linear path, which is shown here by the straight line connecting the 3 points along its path. And then here we have a chart of the path traced out by the link, the joint between links 2 and 3, which basically connects the 2 arms of the mechanism. Now, it traces a circular path because link 2 completely rotates about the origin. And then this is what we obtained once we tabulated all the results in our Excel sheet. In conclusion, mechanism analysis is useful when designing automated systems. It allows for the prediction of any problems, and it allows for very specific position analysis at any point, so that the system can be integrated into a larger automated system without any problems. The problem is that the synthesis of even simple mechanisms is very tedious and complicated when done manually. It takes a lot of time to set up the equations, and there's a lot of room for error with things such as minus signs and parentheses and misclicks and stuff like that when setting up the equations. Now, simulation programs such as SolidWorks and MATLAB are very helpful in this situation because they save a lot of calculation time and they provide a lot of visual representation. It's much better. It helps much better psychologically when you can see the mechanism in action rather than just seeing all the numbers of the path that it traces through.
Thank you.